You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. A value stream is a way of seeing the entire journey an idea takes, from its first spark to its final realization in customer hands or organizational outcomes. The orientation emphasizes that mapping this journey exposes delays, handoffs, and hidden quality risks that piecemeal metrics often overlook. Instead of focusing narrowly on development or testing, the value stream takes a holistic view capturing every activity from request through refinement, build, release, and adoption. By treating delivery as one connected system, leaders and teams can see where work stalls, where rework accumulates, and where signals of progress are weak. Visualizing the value stream is like switching from looking at traffic on one street to seeing the entire city grid. The congestion points, detours, and intersections become obvious. Done honestly, value stream mapping creates a living tool that guides targeted improvements and builds predictability across the whole delivery ecosystem. Boundary definition is the first step in making a value stream useful. Without clear start and endpoints, maps become fuzzy and inconsistent, undermining their ability to guide decisions. Boundaries should represent the first observable step that matters to customers or stakeholders, and the final step where outcomes are realized. For a feature, this might be from initial request to measurable adoption. For a compliance obligation, it might extend from regulatory trigger to verified risk reduction. Defining these points prevents organizations from optimizing only part of the flow, such as development, while ignoring upstream demand or downstream adoption. Boundaries frame the stream as an end-to-end experience rather than a departmental snapshot. By agreeing on boundaries up front, teams ensure that their map reflects the customer's reality, not just the organization's internal convenience. This alignment is essential for trustworthy analysis and improvement. Choosing the right unit of analysis keeps the map consistent and comparable across contexts. The unit is the type of item followed as it moves through the stream, such as a user story, service ticket, or request. Without this discipline, one team might measure tasks, another epics, and a third whole projects, making comparisons meaningless. Selecting a common unit forces clarity about what level of work is being tracked. For example, if feature is the unit, the stream measures how long it takes for a feature request to turn into value, not how long individual commits or tasks take. The unit of analysis must be practical, small enough to show flow, large enough to show meaningful outcomes. By aligning on the unit, organizations make value streams consistent lenses for examining system health, supporting aggregation, benchmarking, and improvement efforts across teams and portfolios. Stage identification brings the value stream to life by naming the actual steps that work passes through, rather than idealized process stages. These steps might include discovery, refinement, build, integration, testing, release, and validation, but they should reflect reality, not aspiration. For example, if handoffs to a security team occur separately, that stage should appear explicitly, even if the official process pretends it is integrated. Naming actual stages makes invisible delays visible. It also prevents organizations from skipping uncomfortable truths, such as untracked waiting periods or repeated review cycles. Stage identification captures how work really moves with all its complexity. By mapping actual paths, organizations gain an honest foundation for diagnosing problems and planning improvements. Without this rigor, value stream maps become cosmetic diagrams rather than diagnostic tools. Entry and exit criteria clarify when work is truly ready to enter a stage and when it is genuinely complete. Without explicit criteria, items churn between stages, as one group claims done, while the next discovers missing elements. For example, development may declare completion, only for testing to reject the item due to absent acceptance criteria. Documenting entry and exit signals prevents this ambiguity. Entry criteria define prerequisites, such as acceptance defined, data available, or designs reviewed. Exit criteria define verifications such as tests passed, approvals logged, or deployment validated. By agreeing on these thresholds, teams reduce rework and improve trust across handoffs. Entry and exit criteria transform the stream from vague flows into accountable transitions. They ensure that when items move, the progress is real, not cosmetic, reducing wasted cycles and strengthening predictability. The distinction between lead time and cycle time prevents confusion about what is being measured. Lead time represents the total elapsed time from request to realized outcome, while cycle time represents only the active working time within that span. For example, if a request took 60 days to complete but was actively worked on for 15, the remaining 45 days represent waiting or context switching. Both measures are useful. Lead time reflects customer experience, while cycle time reveals efficiency within the system. Confusing the two can mislead stakeholders, making delivery look faster or slower than it really is. By separating them, organizations gain a clearer picture of both responsiveness and operational throughput. This distinction also reveals where improvement efforts should focus, whether on accelerating active work or reducing the long waits between activities. Queue and wait analysis shines a light on the hidden places where time accumulates without progress. Much of lead time is spent not in active work but in waiting for reviews, for approvals, for dependencies to be resolved. By measuring how long items spend idle in each stage, organizations discover where aging and context switching dominate. For example, if stories sit in testing queues twice as long as they take to test, the bottleneck is not execution but waiting. Quantifying wait time provides evidence for targeted fixes, such as staffing adjustments, automation, or WIP limits. It also reframes improvement from working harder to managing flow better. Queue and wait analysis reveals the silent thieves of predictability. By exposing them, value streams direct attention where it matters most, unlocking capacity without requiring heroics or overtime. Handoff mapping counts the number of transitions an item makes and identifies the roles responsible at each point. Every handoff carries the risk of knowledge loss, delays, and rework, especially when accountability is unclear. For example, a defect might move between development, testing, and operations multiple times, each transition introducing new misunderstandings. By mapping handoffs, organizations quantify this risk. High handoff counts often correlate with high rework rates and slower lead times. Mapping also clarifies where collaboration could replace formal transitions, reducing friction. By visualizing handoffs, teams can experiment with cross-functional approaches, improving flow. Handoff mapping demonstrates that problems often arise not from lack of effort, but from fragmented responsibility. Reducing unnecessary transitions directly increases both speed and quality, strengthening the stream end-to-end. Rework and return loops quantify how often items flow backward in the stream. Failed tests, unclear acceptance, or broken integrations send work back to earlier stages, consuming capacity and increasing frustration. For example, if 40% of items fail testing and return to development, quality debt accumulates. Logging these loops exposes where expectations are unclear or safeguards are weak. Rework metrics also help distinguish between healthy iteration, where feedback improves outcomes, and unhealthy churn, where preventable defects dominate. Quantifying rework provides leverage for targeted improvements, such as clarifying acceptance criteria, strengthening test automation, or stabilizing integration environments. By measuring backflows, organizations stop treating them as inevitable noise. Instead, they become visible debts that can be reduced systematically, increasing both efficiency and morale. Demand versus capacity signals prevent chronic overload or starvation by comparing arrival and completion rates. When requests consistently arrive faster than they are completed, backlogs balloon and predictability collapses. Conversely, when demand is too low, teams are underutilized and improvement opportunities are wasted. For example, If one team completes 10 features per month but consistently receives 20 requests, queues will double every cycle. Tracking demand against capacity makes these dynamics visible. It also informs trade-offs: either reduce intake, increase capacity, or accept longer lead times. Without these signals, organizations operate in denial, overcommitting and under-delivering. Demand-capacity balance ensures that value streams operate realistically, not aspirationally. It builds honesty into planning, preventing promises that the system cannot fulfill and preserving credibility with stakeholders. Variability assessment examines cycle time distributions and arrival spikes to understand predictability risks. Even if averages look healthy, wide variability undermines trust in delivery forecasts. For example, if half of items complete in a week but the other half take 2 months, stakeholders cannot plan reliably. By inspecting distributions, organizations see whether processes are stable or erratic. Arrival spikes also reveal volatility in demand, which may require buffering or smoothing. Variability metrics highlight where investments in flow stability will produce the greatest gains. They remind teams that predictability is as valuable as speed, especially for strategic planning. Variability assessment prevents false confidence in averages and pushes organizations to reduce spread, building reliability into the system. Predictable flow becomes the hallmark of a mature, trustworthy value stream. Non-functional flows ensure that security, performance, and operability work are visible in the value stream alongside feature delivery. Too often, these flows are hidden, treated as background tasks rather than first-class commitments. Mapping them prevents surprises at release, where systems fail compliance checks or performance benchmarks. For example, if a team maps features but not operability tasks, deployment readiness may appear faster than reality. Including non-functional work acknowledges that reliability is part of value. It also balances priorities, ensuring that technical debt and risk reduction compete fairly with features. Non-functional flows make the value stream honest. They show that readiness is not just about shipping code but about delivering systems that are safe, performant, and supportable. This visibility protects against late crises and builds trust with stakeholders who depend on holistic outcomes. Toolchain and environment touches highlight where manual steps or fragile automation create drag. For example, if builds require manual triggers or deployments depend on one engineer's script, flow slows and risks increase. Mapping these touches exposes where tool integration is weak, where environments diverge, or where automation breaks under load. These pain points often explain why flow feels brittle or slow despite apparent efficiency in development. By visualizing toolchain and environment dependencies, organizations identify opportunities for automation or stabilization. This practice strengthens flow resilience, reducing dependence on individuals and improving consistency. Toolchain visibility also highlights investments with high leverage. Fixing a fragile deployment pipeline may reduce delays across the entire stream. By making these dependencies explicit, value streams connect technical details to system-level impact. Evidence points anchor value stream maps in verifiable data. Each stage should identify where telemetry, decision records, or acceptance signals attach. For example, a testing stage may log pass rates, while a release stage records deployment approvals and monitoring results. By embedding evidence, maps become more than diagrams. They become sources of truth. Evidence points also support traceability, showing how outcomes link to system signals. This strengthens accountability, as stakeholders can verify claims of improvement. Without evidence, maps risk becoming opinion-based representations. With it, they evolve into operational dashboards that guide decisions and track results. Evidence transforms value streams into dynamic tools, supporting audits, retrospectives, and ongoing optimization. It ensures that maps are not just visualizations, but decision-grade assets. Anti-pattern awareness protects value streams from superficiality. Cosmetic maps may look impressive but fail to influence outcomes if they are not kept current or lack actionable detail. Stage names without entry and exit criteria hide real thresholds, leading to churn. Siloed maps that exclude cross-team coupling ignore the systemic nature of flow. These anti-patterns erode credibility, turning value streams into posters rather than tools. By naming and rejecting them, organizations preserve integrity. Value streams must remain fresh, accurate, and honest to retain trust. Anti-pattern vigilance reinforces that mapping is not the goal, improvement is. Without this discipline, value streams become exercises in optics rather than engines of resilience and learning. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Baseline measurement is the first act of turning a value stream map into an improvement engine. Without data on the current state, organizations cannot know whether changes are helping or simply shifting problems. Baseline metrics usually include lead time from request to outcome, the percentage of time spent waiting versus working, the distribution of work in progress, and the first pass yield, which shows how often items move through stages without rework. For example, a baseline might reveal that an average feature takes 60 days, but only 15 of those involve active work while the rest is spent waiting. Capturing this reality can be uncomfortable, as it exposes inefficiencies previously hidden, yet it provides the foundation for prioritizing interventions. Baselines turn vague impressions into measurable truths, giving leaders and teams a shared picture of where they stand before committing to improvement efforts. Bottleneck diagnosis focuses attention where it matters most, the stages that create the greatest delay or rework. In any system, some steps constrain flow more than others. By analyzing where queues are longest or where items repeatedly return, organizations identify true leverage points. For example, if testing consumes 10 days while all other stages average 2, investment in test automation or capacity produces disproportionate benefit. Bottleneck diagnosis prevents wasted energy on optimizing stages that are not constraints. It also reduces frustration, as teams see improvements where delays actually occur. This practice aligns with the principle that systems move at the pace of their slowest step. Diagnosing bottlenecks with evidence rather than anecdotes ensures that scarce resources are applied where they unlock the most throughput and predictability. Policy refinements address hidden causes of instability by tightening or clarifying the rules that govern flow. Entry and exit criteria, work-in-progress limits, and service classes are all levers for stabilizing the stream. For example, if work enters development without acceptance criteria, churn is inevitable. Refining the entry policy fixes the root cause. Similarly, WIP limits prevent overload, while service classes distinguish between expedite items and standard flow. Policy refinements turn abstract principles into practical constraints that guide everyday behavior. They make flow visible and accountable, reducing reliance on individual judgment. This reduces variability and creates fairness, as all teams operate under the same rules. By adjusting policies based on observed data, organizations build resilience into the value stream. Small refinements often deliver outsized impact by preventing the subtle leaks of time and quality that erode throughput. Decoupling strategies reduce systemic fragility by enabling parallel progress without breaking dependencies. Tools like contract tests, adapters, and modular boundaries allow teams to evolve components independently while maintaining compatibility. For example, if a service interface is stabilized by a contract test, both producers and consumers can make changes without waiting for the other. Decoupling reduces idle time, minimizes integration failures, and lowers the blast radius of mistakes. It also enables more predictable sequencing across multiple teams, as dependencies are managed by design rather than by negotiation. Decoupling is not just technical, it applies to processes as well, such as enabling asynchronous approvals instead of serial handoffs. By reducing coupling, organizations increase throughput and resilience. Value streams become less brittle, better able to handle variation, and more capable of delivering improvements at scale without constant coordination overhead. Automation targets eliminate manual steps that are high churn, repetitive, or error-prone, particularly in build, test, and promotion. While human judgment remains essential for ambiguous or strategic decisions, automation accelerates the parts of the stream where consistency matters most. For example, automated regression testing reduces the risk of defects escaping while shortening cycle times. Continuous integration pipelines automate builds and validations, shrinking feedback loops from days to minutes. By identifying where manual work creates drag, teams can focus on automation that produces the greatest leverage. Automation also supports resilience by reducing dependency on specific individuals. It embeds best practices into tooling, ensuring consistent quality even as teams evolve. Automation targets reinforce the idea that the value stream is not just a map but an engine, continuously optimized for speed, safety, and repeatability. Feedback loop placement ensures that learning happens as early as possible in the stream. The further downstream problems are discovered, the more expensive and disruptive they become. By inserting earlier demonstrations, assumption tests, and observability hooks, organizations catch issues before they multiply. For example, showing users prototypes early may reveal design flaws before coding even begins. Similarly, embedding observability into staging environments surfaces performance bottlenecks before release. Feedback loops should be designed intentionally for each stage, providing signals appropriate to the decisions being made. This placement shifts discovery left, reducing rework and accelerating validation. By treating feedback as a structural component of the value stream, organizations transform flow from a sequence of tasks into a learning system. Each stage becomes not just a step forward, but an opportunity to confirm direction. Cadence harmonization synchronizes planning, integration, and review cycles across teams so that work does not stall waiting for others. In multi-team environments, mismatched cadences create idle time. One team may be ready to integrate while another is still mid-cycle. Harmonizing cadences, whether through aligned sprints, shared review checkpoints, or regular integration days, reduces these waits. For example, if all teams demo at the same time, dependencies are surfaced predictably. Harmonization does not mean uniformity. Teams may still work at different paces, but integration points must align. This synchronization reduces starvation and overproduction, where work accumulates unused. By aligning rhythms, value streams move more smoothly, avoiding the hidden costs of asynchrony. Cadence harmonization builds predictability and strengthens trust between teams, turning interdependence from a liability into a manageable feature of system design. Capacity shaping addresses systemic constraints by redistributing skills, cross-skilling staff, or adding resources where bottlenecks persist. For example, if testing is consistently the longest stage, training developers to write more automated tests or embedding testers earlier in development reshapes capacity. Capacity shaping is about structural adjustment rather than local heroics. Instead of overloading one team while others remain underutilized, skills and resources are balanced to smooth flow. This may involve rotational assignments, shared service pools, or targeted hiring. The goal is to reduce imbalance, where one stage consistently throttles throughput. Capacity shaping acknowledges that delivery is a system and must be resourced as such. It turns bottlenecks into opportunities for organizational learning and adaptability, creating a workforce capable of flexing to maintain predictable flow across the entire stream. Governance integration embeds traceability and approvals directly into the value stream so evidence accrues without stopping flow. Traditional governance often relies on pause and resume gates where progress halts for reviews. By embedding governance into everyday tools, such as automated traceability links or inline approval workflows, compliance is maintained continuously. For example, a deployment pipeline may automatically attach logs and test results to audit records. This integration reduces friction while satisfying oversight requirements. It also reassures stakeholders that compliance is not bypassed in the name of speed. By designing governance into the stream itself, organizations eliminate the false trade-off between agility and accountability. Evidence builds as work progresses, making governance a natural part of flow rather than an obstacle. This integration creates a system where delivery is both fast and defensible. Visualization upkeep ensures that value stream maps remain decision-grade artifacts rather than outdated diagrams. Owners must be assigned, update cadence defined, and freshness indicators displayed so that users can trust what they see. For example, a stream map updated monthly may carry a badge showing last refreshed, May 2025. This practice prevents cynicism that maps are decorative rather than useful. Upkeep ensures that flow metrics, stage definitions, and bottleneck data reflect reality. It also reinforces accountability, as owners are responsible for pruning irrelevant details and adding new insights. Without upkeep, maps decay into relics, losing influence. With it, they remain active tools for planning and prioritization. Visualization upkeep acknowledges that systems change constantly, and only living artifacts can guide improvement reliably. It ensures that value streams remain trusted references for decision-making. Outcome linkage ties changes in the value stream directly to customer impact, reliability, and risk posture. Optimizing for speed alone risks delivering low-quality or unsafe outcomes faster. By linking flow improvements to adoption rates, satisfaction scores, incident reduction, or compliance metrics, organizations confirm that value streams improve what truly matters. For example, reducing lead time from 60 to 30 days means little if defect rates climb. Linking outcomes ensures that improvements are balanced and holistic. This practice also strengthens stakeholder support, as leaders can see the connection between operational changes and strategic results. Outcome linkage prevents local optimizations from undermining global goals. It turns value streams into instruments of value delivery, not just efficiency. By aligning flow metrics with business and risk outcomes, organizations make improvements both defensible and meaningful. Portfolio roll-up aggregates a small set of comparable flow signals across multiple products or teams. Signals such as average lead time, percent time waiting, or first-pass yield provide leadership with a high-level view of systemic health. For example, a portfolio dashboard may show that one platform consistently has twice the lead time of others, guiding investment toward shared services. Roll-ups avoid metric overload by focusing only on the most informative indicators. They also prevent distortion by ensuring that aggregated data is comparable with shared definitions across teams. Portfolio-level views help prioritize improvement at scale, guiding where systemic interventions, such as automation platforms or governance reforms, deliver the most benefit. By rolling up value streams, organizations see patterns invisible at the team level, making investment decisions evidence-driven. Remote-ready access ensures that value streams remain inclusive and usable across distributed environments. Maps must be searchable, readable aloud for accessibility, and linkable for integration into asynchronous workflows. For example, a remote team member should be able to access the map easily, search for current bottlenecks, and review summaries without attending every meeting. This accessibility prevents value streams from becoming privileges of co-located staff. It also aligns with modern work realities, where teams are distributed across time zones and contexts. Remote readiness reinforces that transparency and alignment are rights, not perks. By designing maps for inclusivity, organizations maximize their usefulness and preserve fairness. Value streams become shared guides for all participants, regardless of location or bandwidth, embedding resilience and equity into the system itself. Success verification confirms whether changes in the value stream produce measurable improvement. Indicators include shorter lead times, reduced waiting percentages, higher first-pass yield, and clearer predictability across outcomes. For example, if lead time decreases but rework rises, success is questionable. verification ensures that improvements deliver holistic gains, not superficial wins. It also provides closure. Changes are not declared successful until evidence confirms their impact. Success verification keeps attention honest, demonstrating to stakeholders that optimization produces real value. It also strengthens morale, as teams see proof that their efforts improved the system. By embedding verification, organizations complete the loop from mapping to action to evidence. Success becomes not just claimed but demonstrated, ensuring that value stream management remains rigorous and credible. Value stream synthesis emphasizes that improvement begins with honest mapping, continues with distribution-aware analysis, and matures through targeted system changes. Boundaries, units, and stages must reflect reality, not aspiration. Baselines, bottlenecks, and policy refinements provide focus, while decoupling, automation, and feedback loops accelerate learning. Cadence harmonization and capacity shaping stabilize flow, while governance integration and upkeep preserve trust. Outcome linkage and portfolio roll-ups connect operational improvement to strategic results, and remote-ready practices ensure inclusivity. Finally, success verification validates that optimizations reduce delay, rework, and risk from idea to outcome. Together, these practices make value streams not posters on a wall, but dynamic instruments of change. They reveal how work truly moves, where it falters, and how it can be made smoother, safer, and more reliable for all involved. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.